Hello my esteemed viewers. In this tutorial we see how the stresses and strains get shared when a composite section is subjected to loads. By composite section we mean it's a section taken out of a component which is made out of two or more different materials fabricated together in an object for enhancing mechanical properties like strength, flexibility, ductility, and capability against bending, etc. for technical or constructional use. And of course, nowadays composite constructions have become predominant in the construction industry. Different materials remain separated, of course. Different materials are not blended together chemically or metallurgically. They are separated microscopically and don't get mixed atomically. Meanwhile, the bonds between the fabricated materials are not atomic bonds but rather bonds of getting glued together at a macroscopic level. Here in this figure you can see a steel beam and steel beam carrying a concrete slab or concrete slab being placed over a steel beam. In order to have some kind of a bonding, there are nail like things over here welded. They are called as shear connectors and they are provided whenever the beam bends. Whenever the beam bends owing to the load or vehicular load, there will be separation of this slab as well as the beam. So there will be enormous amount of shear that is developed in this particular interface. Of course, the analysis in this example is going to be a little complex and we are not going to deal with this kind of composite action. But however, this serves as an excellent example as to how the composite sections behave whenever they are loaded. Anyway, by nature, steel is very strong in taking tension and concrete is very strong in taking compression. Therefore, whenever a component is subjected to both compression and tension, it is the responsibility of the concrete portion to take up the substantial portion of compression, while huge tension will be taken by the steel. And this is the same thing that happening over here. The compression zone and tension zone will be formed whenever a beam bends. And this is here as we go down this particular axis, tension will increase, and there you will find juvenile wood in the center, which will be very soft, and mature wood will be, or highly seasoned wood will be placed in the compression zone and tension zone. And there are several composite constructions. We can quote several examples from the real world scenario. This is a composite let us say composite bridge that is in construction, and this is already a constructed composite bridge. And here we can see the steel beams running, and atop the steel beam we will find the pavement or concrete slab carrying the road. And here this is a typical a very simple example of a composite section, and this is steel reinforcement which will be taking shear as well as the tension owing to bending, and the concrete portion will take a substantial portion of compression. Here again there is a composite section made out of aluminum and plastic, and here is a shaft section, and here in the core we will see the material which is a little weak in shear, while the edge forms very strong material for shear. And these shafts are subjected to torsion, and torsion we will see later in our continued tutorials in the let us say in the unit where we discuss about the shafts and shaft action and the torsional shear, etc. We will see the shear becoming very critical at the periphery of the component, and at the periphery we have placed here in this particular example a strong steel or hardened steel which will take shear, enormous amount of shear. And here is a composite tubular section. Different kinds of materials are have found sheathing and they have been placed. And here this is another example of a composite section, and if you take a section over here, you will see concrete together with steel. Steel is in good intention, concrete is good intention. Therefore, this kind of construction or this kind of mixing of materials, providing some kind of a composite section is done in order to utilize the best capability of the materials against certain kinds of stresses. And here is a lightweight composite platform. Composite sections. With reference to civil and structural engineering, composite construction typically refers to the use of steel and concrete formed together so that the resulting component behaves as a single element. And this is applicable even for mechanical engineers, mechanical engineering, let us say industrial and production engineering, as well as the aeronautical engineering. Composite materials have made a key role in the sustainability of the components. The aim of composite construction is to utilize the best properties. This is a very important, this is a key point. The aim of composite construction is to utilize the best properties of the different materials and to deliver performance that is greater than had the individual components been used together but not unified. Let us say, had we developed a beam fully made out of concrete, when a beam bends, the bottom zone will be subjected to tension and the top zone will be subjected to compression, and the portion which is subjected to compression will be steadfast, it will remain there, while the portion that is subjected to tension will develop cracks. So there is no unified behavior as far as this particular component is concerned, this particular example is concerned. Therefore, we introduce reinforcement in the tension zone and we will just leave apart only the concrete matrix in the compression zone. In the case of steel and concrete, the best properties would be the tensile capacity of the steel and compressive capacity of the concrete. Let us understand what do we mean by composite action and how do we develop the expressions for stress in different materials. And here is a metal and here is a concrete. Let us say there are two materials and it is subjected to a compressive load P, and this is material 1 and this is material 2, and in the section it will be seen like this. Of course, they are held intact by means of a, let us say, some kind of a connection over here, some kind of a end and some kind of a fixity, and they will not be subjected to any relative moment whatsoever. They will take the force P, load P, as if they are one, though they are different materials. So here comes material 1, here comes material 2 as far as this composite section is concerned. Now, material 1 has the elastic modulus E1 and area of section A1, and material 2 has elastic modulus E2 and area of section A2. Let us say if it is steel, the elastic modulus is somewhere around 200 GPa, and if it is bronze or so, the elastic modulus will be about 100 GPa. Loads get shared. Of course, the total load applied over here will be shared by this material 1 and material 1. They will never be subjected to equal amount of load. And so as far as the displacement is concerned, that is, we will come to that. Load on unit P equal to load taken by material 1 and load taken by material 2. Therefore, P equal to P1 plus P2. So P1 can be written as sigma 1, the stress in material 1 into area of cross section of 1, and stress in material 2 and area of cross section of material 2. This forms the first equation. We are trying to determine the stresses developed in the two materials. This is the punching relation, that is strain in one material equal to strain in other material, because the change in length of one material equal to change in length of the other material. Relative movement will never be permitted because they are fixed their lengths will be same usually, and there won't be any relative movements. We have never seen in real practice whenever a beam is subjected to bending, or whenever a column is subjected to compression, or whenever a tie rod, a tie member is subjected to hood tension, there is no relative movement. That, for example, the reinforcement will never come out and concrete will never get compressed in the earlier instances of the load. Therefore, they will be in tantrum. They will be working in tantrum, receiving the load to the proportion they are worth it. They are capable of. That depends upon their own capacity. But however, the strain is maintained to be same, and that is this composite action. Strain remains the same in both the materials, but the load will be different. Therefore, stresses will be different. Therefore, stresses are designated as sigma 1 and sigma 2. Therefore, strain in material 1 equal to strain in material 2, epsilon 1 equal to epsilon 2, and epsilon 1 can be written as sigma 1 into E1 equal to sigma 2 into E2. Therefore, sigma 1 equal to sigma 2 into E2 by E1, and sigma 1 equal to m times sigma 2. That is, the stress in one material equal to modular ratio times stress in the other material. So this modular ratio, again, the property of both the materials are put to use. For example, steel has 200 GPa and some other material has 100 GPa. The stress in steel will become modular ratio times stress in other material. Here modular ratio happens to be, let us say, if this is 200 and if this is 100, it is 2. Modular ratio is 2. And between steel and concrete, modular ratio will be as high as 10. Okay, we will go through examples, illustrative examples, to consolidate our idea regarding composite sections. Here is a concrete column which is compressed by an axial load P, and the question is, what fraction of the load is carried by the concrete if the total cross-sectional area of the steel bars is 1/10 of the cross-sectional area of the concrete, and the modulus of elasticity of steel is 10 times that of concrete. Here is a concrete column. Here are the reinforcements. There is a load that is being applied exactly at the axis of the concrete column. The total load P is shared by the concrete and steel. This is typical of a composite action. Of course, P equal to PC, the load carried by concrete and load carried by steel. Therefore, P equal to sigma C, the stress in concrete, into area of cross section of concrete. So that will constitute the load, because stress equal to load by area. Therefore, load equal to stress into area. It is something like, it is a simple relationship that we have studied in the past. PS, the load carried by the steel equal to stress in steel and to area of cross section of the steel. This frames into equation number 1. And strain in concrete equal to strain in steel. Therefore, strain is stress divided by modulus of elasticity of concrete, and strain in steel, and it is modulus elasticity of steel. And if we just cross multiply, we will get this is given to be 10 times EC. Okay, therefore we will obtain a relation something like this: stress in steel equal to 10 times stress in concrete, putting this relation in 1, and we have this particular relation. Now it is good enough. If we go back with this relation to equation number 1, we substitute sigma C into AC. In place of sigma S, we will place 10 times sigma C, and this is AC by 10. It is given the area of steel is 1/10 of area of concrete. Therefore, upon simplification, we will find P equal to 2 times sigma C into AC, and sigma C into AC is nothing but PC, the load carried by the concrete. Therefore, P by PC by P equal to half. Half of the load will be carried by the concrete. It is something like this. It's a very simple problem and very ideal problem. Now we will go for a little complexity. A square column is formed by 25 millimeter thick metal casing with outside dimension 250 by 250 and inside dimension 200 by 200 inside dimension, and this is the concrete core which has the dimension of 200 by 200, while it is being encased in a steel metal casing with 250 or 250. Therefore 250 minus 200 will become 50, and the thickness will be shared between two edges, so 50 divided by 2 is 25 and 25, therefore it becomes 25 millimeter thick. It is filled with concrete as shown. The casing has modulus of elasticity of 84 GPa, that is a metallic casing has a elastic modulus of 84 GPa, and concrete core has the modulus of elasticity of 14 GPa. So modulus of elasticity of concrete is typically low when compared to the metal. Therefore concrete happens to be brittle in nature, while metals, almost all metals, are ductile in nature. Therefore the ductility is best utilized, and so also the brittleness, so also the lower value of elasticity. However, the concrete is very strong in taking tension. Due to compression, the column will ooze out. When it squeezes out, assuming some kind of a bulging, tension will develop over here. For example, if I approximately sketch the behavior of this concrete column, it has to buckle like this. Okay, it has to bulge like this, like this. So when it happens so, due to applied loading, there will be tension here. In this surface there is tension, in this surface this is tension, or this particular zone is subjected to tension, so also this particular zone, leaving behind the core which will be in compression. Therefore in order to take up this particular tension, the metals are typically strong. Therefore the concrete is encased in a shell, in a square shaped container, and it is poured. That is the analogy as far as this particular example is concerned. We will just remove this and we will continue with the problem. Okay, right. Similar to previous problem, of course it is numerical values are given. P concrete and P metal, the load taken by concrete and load taken by metal equal to P total applied load. Therefore sigma in concrete into A in concrete to replace this, so also for the metal, and the equation 1 is formed. This is number 1 of composite action, and sigma metal over sigma concrete is 84. This is 84 divided by 14, that gives us 6. Therefore sigma in metal, the stress carried by the metal, stress taken up by the metal, stress developed in the metal equal to 6 times stress developed in concrete. Now we will make use of this relation, and we will go back to equation number 1 and we substitute sigma concrete A concrete 6 times sigma concrete in place of sigma steel, just now we have derived, and A, area of cross section of the metal, equal to P. It is 5.6. Stress is given into 200 square, because it is a square section, 200 square, that is the area of concrete. And as far as steel is concerned, steel casing is concerned, it is 6 times sigma in concrete into 250 square minus 200 square. 250 square, the outer dimension of the square box, minus inner dimension of the square box. This will give annular area, or the area of the let us say container, which is a metal casing with a particular thickness. Thickness happens to be 25 millimeter, equal to P. And if we simplify this, we will get P equal to 998 followed by 4 zeros, and when we divide this by 1000, we will get 980 kilonewton. And that was the question. Of course, that was the question. The question was find the maximum possible load P on the column if the allowable stress in concrete is 5.6 MPa. We could have continued this problem and we could have found out what is the stress in steel, what is the stress in the metal casing, by making use of this. So in the metal, the stress will be 6 times 5.6. Right, anyway, that is given, therefore we have not found it out. Now we'll go for the third problem. An RCC column of section 230 millimeter by 400 millimeter. 230, we have taken only section. Okay, we have not shown the isometric view of the column for obvious reasons. It's not required, we have understood. This is provided with 6 bars of 20 millimeter diameter. 1 2 3 1 2 3 6 bars, steel bars, of course. The column carries a load of 400 kilonewton. This is in relation to the previous problem. This can be said to be an economical design. We have placed only steel rods to take up the necessary tension that would develop at the periphery due to buckling of the column or due to bulging of the column. Find the stresses in concrete and steel bars. Given elastic modulus of steel is 210 GPa and elastic modulus of concrete is 15 GPa. So we will develop. First of all, we will find out the area of cross section in order to simplify, in order to make our further calculations easy. So we will be ready with this numerical things. So 6 into, there are 6 bars, each of diameter 20 millimeter. Therefore pi d square by 4 is the area of cross section of a 1 bar, and multiplied by 6 we will get the area of steel hidden in this concrete matrix, hidden in this particular area. And you can see they are not chemically blended. Steel is not chemically blended with concrete. Instead it has been held tightly by the bond action between concrete and steel, but it is there as a different material and it is available in the area of cross section. That is very important, and this is atypical of a composite section. Area of concrete AC, once again 230 into 400, but this is not the fullest area. Fullest area is not covered by the concrete, and we have to lessen the area of steel in order to get back the area of concrete alone. So this is total area of cross section available minus area of steel, because area of steel is to be removed and there will be holes remaining. And if you pull out these bars, okay, that is only an analogy. Okay, 90,000 something, this is square meter, this is the area of concrete. Therefore strain in steel is strain in concrete. This is another punching equation. Therefore sigma s by es equal to sigma c by ec, by making use of fundamental Hooke's law, and we will get sigma s equal to es by ec into sigma c. Es is 210, ec is 15, and we will get 14 sigma c. Therefore sigma s, stress in steel, is 14 times stress in concrete. Load taken by concrete equal to load taken by steel equal to total load, and we will substitute now sigma c into AC for PC and sigma s into AS for PS equal to P, and we will directly substitute over here because we know the area of cross section, and sigma c remains to be unknown. This unknown is removed by placing 14 times sigma c obtained in the previous step. So equal to 400 into 10 to the power of 3. This is the applied load, 400 kilonewton converted into Newton, and we will get sigma c upon simplification to be 3.43 Newton per millimeter square. Therefore stress in steel is 14 times 3.43 stress in concrete. It will get us 48.02 Newton per millimeter square. A composite section comprises of steel tube 100 millimeter internal diameter. This is the steel tube, 100 millimeter internal diameter and 120 millimeter external diameter. This is fitted inside the brass tube of 140 millimeter internal diameter. This is 140. This is 140 millimeter internal diameter. This one, the outer tube. Okay, and 160 millimeter external diameter. This is the section. Now you can see the gap. So this will only tell us that they are not metallurgically blended. Okay, it provides a composite section, that's all. So here is a gap, and as far as the materials are concerned available in the area of cross section, a hollow circular section of a steel tube and a hollow circular section of the brass tube. and they are tightly fitted with fasteners at the ends, and the load is applied. And there is no relative movement. It is not that steel tube, say a brass tube, unable to sustain the compressive load. Okay, just lessening in its length before this slowly lessening its length. It's not like that. It's not like that. The strain in tube should be equal to strain in brass tube should be equal to strain in steel tube, in order to see no relative movement between them. That is the idea. So this is the cross section, and we will calculate the area of cross section. Area of cross section of the steel tube is pi by 4 into 120 square, outer diameter square minus inner diameter square, in order to get this particular area of cross section. It happens to be 3455.75 millimeter square. Area of cross section of the brass tube is pi by 4 160 square minus 140 square. We will get the annular space area of this particular cross section. So that happens to be 4712.38 millimeter square. And we will continue with the second punching equation, that is strain in steel equal to strain in brass, and we will substitute this, and we will get to know the relationship between stress in steel and stress in brass, and this is obtained by this ratio, ES by EB. Alright, load borne by steel equal to load borne by brass equal to total load applied over the composite system or composite component. Sigma S into AS, sigma B into AB, B for brass and S for steel. 500 into 10 to the power of 3, because 500 kilonewton has been applied as a compressive load. So 2 times sigma B we have obtained over here, sigma S. In place of sigma S we have placed this, and other things we have made it to remain as it is, and upon solving this, after substitution of the appropriate values, we will get sigma B equal to 43.101 MPa. And if you continue, we will get sigma S equal to 2 times 43.01, that is 86.02. Load carried by brass tube equal to 43.01 into its own area. This is the stress into area. We will get 202.68, and load carried by steel tube equal to 86.02 into its own area of cross section we will get. And a little consideration will show that when you add them together, you will get 500 kilonewton that is being applied over the system. As the strain is same in both the metals and also the length, decrease in length, the question says find the decrease in length of the sections or the materials or the components, tubes. Anyway, as the strain is same both the metals and also the length is same, the strain is same, therefore change in length must be same. So decrease in length of the brass tube equal to decrease in the length of the steel tube. Therefore, change in length of brass tube equal to change in length of steel tube, and we will make use of this because both of them are same. Stress in brass tube into length, its own length, divided by EB. This is taken out of an expression we have derived in our second tutorial, wherein change in length of a member subjected to compression or tension equal to PL by AE. P by A is replaced by sigma B. That's all. PB by AB is replaced by sigma B. So sigma B into L or EB, and we will upon substitution of the values, appropriate values befitting this particular notations, we will get the change in length of both brass tube as well as steel tube to be 0.645 millimeter. We will go a steel tube 30 millimeter in internal diameter and 40 millimeter in external diameter contains a copper rod of 20 millimeter. This is the copper rod of 20 millimeter diameter. The tube is 500 millimeter long. The length from here till here is 500 millimeter. That is the length long, and closed by rigid washers. Here is a washer and here is a washer, and that are fastened by nuts. So this particular rod has threads at the end, and this is rotated. till the system is held fast very tightly, okay, so that no relative movement will occur, and that are fastened by nuts threaded on the copper rod. The nuts are tightened until the compressive load on the tube is 30 kilonewton. So this problem stands to be a fine example for how to create change in length, how to create some kind of a strain, thereby creating stress in them. So it's a reversal procedure. The nuts are tightened until the compressive load on the tube is 300 kilonewton. Of course, the nut is attached to the threads that are made on this particular rod, and the rod goes inside this particular tube. When the nut is rotated, the rod will go for compression, the rod will go for tension, while the tube will go for compression. Okay, we will just understand how exactly one component will be subjected to tension and the other component will be subjected to compression. And here there is no sharing. Okay, they will take the compression, decrease in length or increase in the length proportionate to their capacity. Here the deformation is shared. In the earlier case, the load was shared by the two materials. Here the deformation will be shared, and we will see that. What are the stresses in tube and rod? Find the increase in these stresses when the nut is fastened to further tightened by 1/4 of a turn. There are 4 threads per 10 millimeter. That means 4 threads per 10 millimeter means one thread will take this particular nut by 10 by 4, that is 2.5 millimeter, and it is not turned completely, it is turned just by 1/4 of a turn. Therefore the deformation that is given excessively is 1/4 of 2.5 millimeter. Okay, whatever that it comes. Okay, that will subject the copper rod into tension, huge tension, and the steel tube into huge compression. We will see that how exactly this happens. So here is an example. When we rotate this nut, the stud carrying this particular nut, the rod like thing, which will be provided with threads, will go for tension, and this plate will get fastened tightly with the tire, and so also the tire rim will be tightly fastened to the shaft, hub of the shaft. And here there is a clear example. When we rotate this nut clockwise, this stud will be subjected to tension while these two pieces will be fastened tightly together. And if you remove this system and had this been a wooden ring like thing, we would have seen impressions created by this washer. That means to say that this member will be subjected to compression while the stud will be subjected to tension. And here again we can see there are two components which are clamped together by a clamping force owing to rotation of the nut. The nut will be rotated, force will be applied through our arm, and it presents some kind of a torque, and this nut in the melee will go for tension. When the nuts are tightened, the rod will be subjected to tension while the tube will be subjected to compression. The shortening of the tube is independent of lengthening of the rod. See, here it is. Here is the magic, and here is the gist of the idea. But with the absence of any other external loads, the compressive load on the tube is equal to tensile load on the rod. So when we induct or when we impose the change in the dimensions by external rotation or some kind of a force or some kind of a moment, it is the deformation that is getting shared, that gets shared, and the loads will never be equal to. Okay, the compressive load on the tube is equal to tensile. Yeah, the loads will be equal because they will be pressed by the same amount. Whatever the tension force that happens to this stud will be the compression force for this component. Whatever the tension force that is suffered by this particular stud will be the same amount of compression as far as these two members are concerned. That is the logic. Therefore, first of all, we will find the area of cross section of the tube. It is pi by 4 into 40 square and minus 30 square, outer circle square minus inner circle square. Thereby we are getting the annular area where the material is present, 549.8 millimeters square, and area of section of the rod is pi by 4 into 20 square, because the rod measures 20 millimeter in diameter. So we have got the area. Now we will put up this equation. You may recall that in the previous expression we wrote strain in steel equal to strain in concrete, but here we write tensile force in rod equal to compressive force on the tube. It is just a reversal mechanism. So PC equal to PS. Therefore we will substitute in terms of stresses, sigma C into its own area equal to sigma S into its area of steel. We will get an expression for sigma C equal to 1.75 times sigma S. When the compressive load on the tube is 30 kilonewton, this is the stresses, this is the applied load, maybe by rotation, obtained by rotation, of course. 30 kilonewton of compressive load is achieved. Therefore sigma S equal to, we will get this expression, 30,000 divided by its own area, and sigma C is 30,000 divided by 314, 95.49. that is the stress. And now the rod is having now it is rotated a quarter turn as per the problem. The rod is having 4 threads per 10 millimeter. That means if you completely rotate 4 threads completely, there is a tension amounting to 10 millimeter of elongation. That is the amount of stress. That is the amount of stress that is being generated. The stress that is needed in order to have a change in length of 10 millimeter. Okay. Therefore, one turn will cause a movement of 1/4 into 10, 2.5 millimeter. If one turn is to be completely rotated by the nut, we will have 2.5 millimeter of lengthening, or that amount of the stud will protrude out. Okay. In this case, the nut is further tightened by only quarter turn, not even a complete turn. Therefore, the movement of the nut in axial direction is 1/4 of 2.5 equal to 0.625 millimeter. We will make use of this. Reduction in tube length plus extension of the rod equal to 0.625. So this is another punching equation. In cases where the change in dimension is induced, here it is induced by rotation of the nut. Okay, rotation of the nut will compress the material, say the component that are to be fastened, while it will apply some kind of a tensile force for the stud carrying the nut. So it is sigma S into 500, the length is 500 in both the cases, divided by 200 into 10 to the power of 3, sigma C 500, 100 into 10 to the power of 3 equal to 0.625. This is change in length in copper tube, and this is change in length in steel rod, which is equal to 0.625. How much they elongate and how much they compress, for this question answer is to their capacity. 2.5 into 10 to the power of minus 3 into sigma S, 1.75 into sigma S, because 1.75 into sigma S we have proved in the previous step. So 5 into 10 to the power of 3, 10 to the power of 3 will come up equal to 0.625. And if we calculate further, we will get 11.25 into sigma S equal to 625. So 10 to the power of 3 will get cross multiplied, and 0.625 will become 625. And upon simplification, we will find sigma C equal to 97.22. So it suddenly rises from the earlier value. What is that? 54.56 was the earlier value. 95.49 was stress in copper tube. Now stress in copper tube will become 97, a rise of around 4 MPa by just a quarter turn, and this is a rise by around 20 MPa due to a quarter turn. And you can notice there is a steep hike in the tensile stress, that is generated in this steel rod. So with this we complete this particular tutorial, which exclusively discussed very clearly what do we mean by composite sections and the stresses that are developed in a composite section in different materials. If you have liked this video, kindly subscribe to my channel, and until I come out with the other tutorial which will be exclusively on temperature stresses, bye, and thank you for viewing this tutorial. Thank you.